In this video, I'm going to talk about magnetic induction. Whenever there's a term induction, there's no actual voltage source. The EMF, which stands for the electromotive force, or which is the voltage, that one is generated by the changing magnetic flux. So let me explain this one here. So in this case, we have a coil, and this coil is connected to an oscillating voltage source. When I say oscillating voltage source, that means the voltage or the current is not constant as the time passes by. So what happens when a current passes through a coil? When the current passes through a coil, then there's a magnetic field. And as the magnetic field depends upon the current, the magnetic field is changing with respect to the time. And then this magnetic field, or we call the flux, some of the magnetic fields also passes through a secondary coil. And these two coils are by no means connected to each other. So as there are magnetic fields produced by the first coils, there will be some magnetic flux passing through the second coil as well. And because of the changing magnetic flux through the second coil, we get an induced EMF, or there is a voltage difference between these two terminals, or there will be a current passing through the circuit. And this current we call as an induced current, or this voltage between the two terminals or the two ends of the coil we call as a EMF, electromotive force, or the induced EMF. All right. So this EMF is generated again by the changing magnetic flux. So there must be change in the magnetic flux. That's the origin of EMF. And there are many the devices, the appliances, which are based on the concept of the electromagnetic induction. The one is transformer, the metal detector, the wireless charger, magnetic braking. So these are the devices that works on the principle of induction. So there are two types of inductance. The one is mutual and the other is self. And we'll go one by one. The mutual inductance, in this case, we have at least the coils or the system here. So here we're considering the two solenoids or the two coils which are placed next to each other. And again, this first coil, there is a changing current, or it is connected to an oscillating the voltage source. And because it is connected to an oscillating voltage source, the flux passing through this coil is changing with respect to the time. And this some of the flux also passes through the second coil, or coil 2. And because the flux through the coil 2 is also changing with respect to the time, there will be a voltage drop across these 2 points, or there will be a current in this coil 2. And that current, as I mentioned before, will be called induced current, and the voltage drop between these 2 points or across the coils we call as an induced EMF. So what is the magnitude? How do I find out the value of the induced EMF? So the induced EMF in coil 2 is given by this expression here. This EMF epsilon 2 1, that means the induced EMF in coil 2 due to the coil 1 is given by rate of change of current that is happening in coil 1, and then this term here is a constant term that is called the mutual inductance. And now you might be wondering about this negative sign. This negative sign is coming from the Lenz's law, or if you want to understand the meaning of this negative sign, so this negative sign always try to oppose the cause. So let's say, for example, here, if the current or if the magnetic flux through this coil is increasing, then the induced EMF will in this circuit will be in such a way that it will try to oppose the increasing magnetic field. or if the magnetic field in this one is decreasing, then the induced current in this circuit will be in such a way that it will try to increase the magnetic field. So in all cases it will oppose the changes. And do not forget to watch my Faraday's law video and the Lenz's law, the video, to understand the meaning of this negative sign in detail. Okay, so this M is the mutual inductance between the two coils, and this mutual inductance depends only upon the geometrical parameters. It does not depend upon the current. It does not depend upon the strength of the magnetic field. It only depends upon the geometrical, the parameters. And it also represents the efficiency of the coupling. For example, if these two are close to each other, then the flux linkage into the second coil will be more, or there is a better or more magnetic flux passing through this one, so the mutual inductance will be greater. So the higher the M, which is the mutual inductance, represents the greater induced EMF in coil 2. And now about the unit. The unit of the mutual inductance is Henry, and we can derive the other units of the Henry. For example, what is the unit of the induced EMF? That is the voltage times second divided by the current. So that is another unit. And voltage divided by current, what is that? That we call as an ohms. So these are also the units. Or this Henry is related to the voltage and current by this way, or by ohm and the time this way. So these are the three, we can say, the units of the magnetic induction. And also, so mutual inductance does not depend upon whether you pass the current through the coil 1 or coil 2. If there is a changing current in this coil 2, then even in that case the mutual inductance will be the same. Again, the mutual inductance simply represents upon the geometrical parameters, doesn't depend upon the voltage and the current. Just like the capacitor. If you look at the definition of the capacitor, is Q, the charge, divided by the potential difference. Does it depend upon the charge and the potential difference? No, it only depends upon the geometrical parameters. For a parallel capacitor, it only depends upon the area of the plate and the distance between the plates. Okay, and the same way, if there are two coils placed to each other, then the mutual inductance only depend upon their geometrical parameters. Okay, so again, I mentioned earlier that the negative sign in this equation here, or for example in this equation, means that the induced current will have the direction in such a way that it opposes the rate of change of current in it. Okay, and I will explain in the later videos. We'll give you more examples of this one. Okay, so also we can write down, if we have a changing voltage or an oscillating, or if this coil 2 is connected to an oscillating voltage, then in that case we can write down the induced EMF in coil 1 due to the coil 2 as this one. So what does this mean again here? That's the induced EMF in coil 1 due to the coil 2, and that is given by the M and this term here. That means the current is passing through the coil 2, and it's not a constant current, it is an oscillating current. And because of the oscillating current in coil 2, we have an induced EMF in coil 1, and the value is given by this equation here. So depending upon the appliances and the situation, in some cases we need the higher M, higher mutual inductance, or the coupling efficiency of the magnetic flux is more desirable. For example, in a transformer, we need the high value of the magnetic inductance. But in some cases, for example, electric dryer, we need the as low m as possible. And because if this value in this in the case of electric dryad, if this value is higher, then this induced EMF will be so high that it can damage the device itself. Okay, so depending upon the situation, sometimes the we might need higher value of m, or we might need the lower value of m. So if you look at the dryad, electrical dryad, the coils, these coils are counter wounded or intertwined, so that the induced EMF produced by one coil cancel the induced EMF by the other coil. So that's the reason they counterwind in this fashion here, just to cancel the induced EMF produced by one coil by the other coil. Okay, so that is this video. In the second video, I'm going to talk about the self induction. But if you have any question, please write to me or write down in the comment section below. Thank you very much, and I will see you in the next video.